Welcome back to my first and most likely the last tutorial of OpenAL. OpenAL stands for Open Audio Library. It's kinda similar than OpenGL, except this is for audio, obviously, and it is capable of creating three-dimensional audio. That pretty much means that unlike the SDL mixer, which we have used so far to create audio, you pretty much define the position of the sound source in the three-dimensional space. I don't know, 1, 0, 0. That means that it is in the positive x-axis 1 unit long. It uses similar naming convention and coordinate system convention and basically everything than OpenGL. So it will be pretty simple to learn OpenAL after OpenGL if you already know OpenGL. So you define the position of the source, you define the position of the listener, you tell what music or what buffer basically the source should play, and pretty much it does play and calculate what speaker should contribute how much. So basically if the sound is left to you, then the left speaker will be a little bit louder than the right speaker. Another thing is that if the sound source is actually far away, it gets less loud, so basically quieter or more quiet as you like it. And basically, so because similarly than light in the graphics, sound has an attenuation factor, and you can actually set the equation about how much it should attenuate according to the distance. More of this refer to the manual which is on the OpenAL page. But actually first, before I go into any OpenAL, we have to load the WAV or wave file, because OpenAL, similarly than OpenGL, doesn't have high-level function to handling sound. Because OpenGL doesn't have high-level function to rendering models, we have to write an object loader. We have to write a wave loader in here to basically load a wave file and able to play it. Obviously there are libraries which are capable of loading wave file, like ALUT, which stands for OpenAL Utility Toolkit. This is similar than GLUT, if you know that GLUT. So it has a few useful functions, but I decided to just use OpenAL without any additional library. Alright, so I made actually a little bit of presentation about binary file handling, because a wave file is actually a binary file, and so far we haven't actually, none of the tutorial handled wave files. So I made a little presentation, not too much, don't worry, just a little bit. Probably you already know this stuff. Okay, so if you create a variable, like integer variable, like 1020 with the number 1023, it will look something like this in binary if I don't screw it up, which is actually possible that I did, but I think I didn't. Okay, so this is somewhat how it looks like in the memory. An integer is 4 bytes long, so 4 bytes, and the 1023, if I calculate correctly, there are 8, wait, no, I think this is a 10, so it should contain all zeros and then 10 ones in the end. So this is what 1023 should look like, I believe so. Okay, and yeah, that's pretty much it. And if we just use bytes, so in case of the first byte there is a 0, in case of the second byte there is a 0, in case of the third byte there is 3, because 1 is 3 in binary, and in the last byte, or 1 is 255. So this is how it will look like in bytes, because I show you, because this is how we will read in from the file with bytes. So for example, if we read a number 1023, then we basically read 003 255, or in my case, because I have little in endian machine, I will go into the endianness in the next tutorial, I actually reverse this order. Anyway, so let's see the big endian versus the little endian. So this endianness is a weird thing, and your computer can store the number as a big endian. In that case, it stores, like you would expect, a lot of 0, for example in case of 1, a lot of 0 and then 1 in the end, very end. So in this case, this is actually a little endian. This is actually a big endian number right here, because it stores the number as we would like. So the most significant byte is actually contain the biggest of the numbers, so the most significant decimals of the number. I'm not sure if I should take this. Anyway, so I'd rather show you an example, because I can't really tell the definition. But in case of little endian, the byte order is actually reversed. So let me just show you. For example, here is an integer number, as you can see, and this integer number has 4 bytes, about this. As you can see, there is 4 bytes. In case of the big endian, we have a lot of 0 and then a 1. So 0, 0, 0, 0 here, and then a 1 in case of number 1. But in little endian, this is a little tricky, actually everything is reversed. So the last byte become the first byte, like this. This become this. Okay, something like that. Oh, this is what I forgot. Okay, so this is it. As you can see, the byte order actually reverses. So instead of a lot of 0 and then a 1, in case of a little endian, you have some zeros, a 1, and then a lot of zeros. So 7 zeros, a 1, and then a lot of zeros, because the byte order is actually reversed. Okay, and now it's time to find out what kind of endianness your machine actually has. So here how we can find out actually. So we create an integer with the number 1, so similarly like I did here, and we basically check if the number 1 is in the first byte, and if it is in the first byte, then we know it's a little endian. If it is in the last byte, so the first byte is 0, then we know that we have a big endian machine. So let's write a function immediately for that, because it could be important later on. So bool and is big endian. This is the function name, and obviously it's return true if it is a big endian and return false if it is a little endian. So how can we find out? Basically I create an integer as I said, so int a, and this will be equal to 1. Okay, and now check the first byte of it. How we can check the 1 byte of a number? Basically we can access to the byte, we can access to this integer as a char array. So let me immediately do that. I cast the pointer to the a as a char array, so the pointer of the integer as a char pointer. So pretty much we have a char array. Now I can actually get the first, second, and third and fourth byte from it. Like this is the first byte, this is the second, so on. Okay, but I need the first byte and check if it is 1. So because it's a boolean function, I can pretty much return the opposite of this, because if the first byte is 1, then if the first byte is 1, then this is a little endian. But actually my function name is called is big endian, so I have to negate the result. So pretty much this is how you can find out if your machine is big endian or little. Let me write out what my machine is. So if is big endian, so if I have a big endian machine, then I write out big endian as I write out little endian. Little. Right, so let me try to run this program right now. I just search a terminal right here, and I go to my desktop. Here is the terminal. So I go to my desktop and compile the program called OpenAL. I don't need any flags right now, because this is just a standard C++ program. There is nothing else to it. And as you can see, my computer is actually a little endian computer. So it means that the byte order is actually reversed. Right, so this was pretty much one important function which we will use later on. Okay, let me go on and see how we can convert from a character array to an integer, because as I said, we will read the number like this, 003,255. How can we know from this number that this actually want to represent the number 1023? So how can we convert it? Basically we get this char array which contains the 4 numbers, or in case of short it's just 2 numbers, but it doesn't really interest us now. And then I access this integer as a character array, similarly than I did earlier. And then I pretty much just copy in the bytes to the integer as a character array, and then basically the integer will contain the correct number. Of course, in case if you have a little endian machine and the number is a little endian as well. So the number is actually a little endian because according to the WAV definition right here, or format definition, or what is this, all numbers are actually in a little endian format. So it's okay for my machine, but probably if you have a big endian machine, or someone have a big endian machine, the byte order is actually reversed. So in case of a big endian, we will copy the bytes like this. So we get the false minus I minus 1, basically, I think, or 3 minus I element, and that will be pretty much how can we access. Right, so let me actually write a function which converts a character array to an integer. So void, actually integer, and char to actually call it convert to integer. Right, and this will wait a character array buffer and the length. Okay, so let me try to convert it. And as I said, we do pretty much the same as here. So I access the integer as a character array, so I cast it to a character array and get the address of the integer. So now I access the integer as a character array, and I can use a for loop right here. So for int I equals 0, I less than the length of the number I plus plus. I need this length, so I don't want to copy all 4, because in case of the number of channels in the WAV file, it's actually just 2 bytes, so I need this length. Right, so I access the ith element, and then I set it equal to the buffer I. So I do exactly the same as I showed you here. I access the integer as a character array, so now I have 4 elements in here, and pretty much I just copy the corresponding elements to the corresponding bytes of the integer, and then at the end it contains the right number, so return A. But as I said, if we have a big endian machine, we have to reverse the order. So if not is big endian, because it works if it is a little endian, then I do this, what I showed you here. Else, I almost do the same, so actually I so much almost do the same that I will copy this, but instead of copying the first byte into the first place, I copying the first byte to the last place. To do that, I pretty much get the 3 minus ith element. Actually, I think that would work, but here which I wanted to write, 3 minus ith element. So this is pretty much how we can convert to an integer, and I'm pretty sure it's supposed to work. Actually, let me find out that if it will work or not by creating this array right here, like I had in the very first dia right here, with the number 0, 0, 3, 255, but I said I have a little endian number, so I reverse the order, 255, 300. So I create a char buffer with 4 elements, and the 4 element will be 255, 300. Okay, and let me try to write out this number. So convert to int, and I convert the buffer to an integer with 4 elements. And if everything goes correctly, then I will get a 1023. If not, then I don't. Okay, I forget to create the a variable, so int a equals 0. I have to initialize it to 0, because in case of 4 bytes it doesn't matter, but if you have just 2 bytes, so it's a short number, then the 2 byte will remain some random number, whatever happened to be on the memory place. Now I can compile and run it, and indeed I get the number 1023. So far we have made a great progress, but now we actually have to load in the WAV file. So I make a function which does this, char and load WAV file. So load WAV function will obviously wait for the file name, so const char, and let's call it fn, like file name. Okay, this next parameter are references to data which we want to give out from the function. Obviously we want to give out the actual data which we have loaded as a char array. Then we want to give back the number of channels, so int channels, and then I want to give back the sampler rate of the WAV file, so int reference sampler rate. Then I want to give back the bit per second, so int reference bit per second. And lastly I want to give back the size of the return data, so int reference size. Right, so here is the load WAV function, and here is the definition of the WAV file. I download it from this site right here, and I just pasted it into this document because it's easier to read in here. Okay, and exactly this is how exactly the file is structured. So 4 bytes, this second number is the byte, we don't care about the first number, this is the offset from the beginning of the file. We will just use the read, and it will automatically set the offset to whatever we want. So basically if we read 4 bytes, then it will jump to the 4th byte and we will read from there. So we don't care about this first number, but we care about greatly with the second number, which is the number of bytes the current data is. For example, the first data in a WAV file is actually 4 bytes long, and it contains the letters RIFF. The second number is 4 bytes long, and it contains a size. We don't really care actually about this size, because we don't. Right, we don't care about the format, we only care about just a handful of data from this lot of data, like the number of channels, the sample rate, and the bit per sample, the size of the data, this, and the data itself. We don't care about anything other actually from the WAV file. So let me actually do that. It's pretty simple. we obviously need an IF stream, so an input file stream to read in. I already included the F stream header file, so it will be pretty simple. std if stream, like input file stream, we'll just call it in, and this will with the file name fn, and the second parameter is actually we should tell the if stream, so the file stream, that we are actually reading in a binary file. But I'm not sure this is necessary, because if we use the read member function, which I believe we read the bytes unformattedly without any flags, but just to make sure I will just say iOS binary. This is how you can tell that this is a binary file. iOS binary. This is basically a flag. So we set the binary flag, so ifstream will know that we are reading a binary file. Okay, and that's pretty much it. So how can we read bytes with it? We use the read member function. So in.read, and the first parameter is actually where we want to read. Actually let's create a buffer, char buffer, and with 4 elements, because the 4 is the biggest number you can find in the second row right here. As you can see, you have 2, 4. The data is actually bigger, but we don't read into the buffer, we will read into the another variable. Right, so we have the buffer, and so the first parameter is the buffer, and the second parameter is actually how much bytes do you want to read in. We want to read in 4, because as you can see, the first is actually representing the number 4. Okay, so I read in 4 bytes, and it should, if in case of a WAV file, it should contain the number letters RIFF in ASCII coding. So let me write out std cout and write out the buffer 0, then the buffer 1, 2, 3, and if everything goes correctly, and I save out a WAV file, so 1, 2, 3, and make a new line right here, so std end line. So if everything goes correctly and I save out a WAV file, then we get the RIFF letter. So let me save out the WAV file. So I open up Audacity. This is a free program, cross-platform, to handle music and all kind of different files. And I generate a sound, this second one. Not sure if I can translate it. And I only generate 5 seconds of sound. I don't need that long a sound. So let me show you what this sound like. Okay, this is how it sounds like. So let me export it. So file, export, and in my desktop I will export it as test.wav file. Make sure that you select the WAV format right here in the bottom right corner. Okay, and of course I overwrite it. Just make sure you don't write anything into any of these, because if there is something, then it will be in the header file if you write anything anywhere, and that will pretty much through our WAV loader, and if there is something, then come here and delete it. You don't need it. Okay, and press OK, and pretty much you have exported the file. And now I can exit from this program, and let's try to load this file. So load WAV, and I load the test.wav file. Oh, and we need a lot of integer as our next parameter. So in channel, then I need sample rate, then I need the bit per second, and I need the size, if I am correct. What this parenthesis doing here? Okay, so channel, sample rate, bit per second, and size. Alright, and now if I can compile and run this program, we get the character RIFF. Perfect. Okay, I will not write out everything. You should actually check if this number is RIFF, and if it is not RIFF, then exit from the WAV loader, because it is not a valid WAV file. But for simplicity and for the sake of time, I will omit the error handling from this whole WAV loader. So that's not a good practice. Actually, let me write here just one error handle, and I will use I will use the file C string header file, and the C string header file contains a function called strncmp. Okay, this is the name of the function, and it compare to string, but not compare the entire string, but just the for n character. So so buffer, this is one string, and then RIFF, this is the other string, and if it is returned and if it is not equal with 0, then they are not matched. So actually there is another parameter, how many characters, 4 characters. Then I make an std cout, the strings doesn't match. Okay, and std end line, and just return from the function with null. Okay, actually maybe we should write that this is not a valid wave file. Okay, you should put this error handling into other places, but let me try to run it and see. Okay, it doesn't write out anything, but let me load, for example, what else in my folder, what else in here in my desktop. Let me try to load the a.out, so not valid wave file, a.out. Okay, and if I try to load a file which is not a wave file as a wave file, it will write out that this is not a valid wave file. Perfect. You should check other things. I will show you what else later on, but I will only put this one checking. This should pretty much be enough. Okay, the next is the size. We don't really care about the size, actually the header size, so I just read into the buffer 4 bytes and just omit. We don't do anything with it, we just read in. The next is the format, so in the read, and again buffer and 4. Alright, read and 4 bytes. Okay, and you should check if it is wave, so if it is contain the letter wave similarly than I did here, just with wave. The next is, we don't have anything else in here except if you put something into that comment section in the Audacity, then it puts somewhere like here, or maybe here is the extra parameter. I don't know, it puts something somewhere and I don't want to care about that. The next 4 byte, so again I read in the 4 byte, should contain the constant fmt and the space. The next is again 4 byte and it should contain 16. So this is 16. You want to check for this, because if they are not these values, then you don't have a valid wave file. The 16 could be different if the file is actually compressed, the wave file. But we use PCM format, which is basically the net converted format. If it is anything else, then you have a problem. As you can see, 16 for PCM. The next is 1. Okay, and the only difference here, you load 2 byte, because you see here it's right 2 byte, and it should contain the number 1. Okay, the next is again 2 byte, and this is something we care about. So let me copy this. This is the number of channel, 1 for mono, 2 for stereo. So make the channel equal to convert to int buffer and 2. Right, so we convert it to an integer. 2 is the size, obviously, because we read in just 2 byte, and the buffer, and make it equal to the number of channels. So later on we can use it outside of the program to tell OpenAL that this is a mono or a stereo, obviously. Sample rate, this is again something we care about, so let me copy this in the read. And so this is something that we care about, so make the sample rate equal to convert to int buffer 4. Okay, I converted to an integer as well. The next byte rate and block line we do not care actually, so let me just copy 2 of these lines, because one is 4 byte, one is 2 byte. We don't care about these data either. By the way, you can omit reading in the data which you don't need by positioning the pointer, file pointer, to wherever you want with seek, but I think I just read in, so maybe later on we can check for this data and use these data for something. It doesn't really have too big of an overhead, because obviously the entire file is cached in this case from the hard drive, so we don't access the actual hard drive. Okay, bits per sample, this is again something we care about. And how many bytes is it? Bits per sample, 2 bytes. Okay, so let me just copy this, and the bit per sample is actually a convert to an integer buffer 2. This is it. And what else do we have here? Extra parameter size. If PCM, then this is doesn't exist in this is either. And if you don't write comments, wherever I said you don't write comments. The next is the subchunk to ID. Okay, this again something we don't really care about, but this contains the character data, and if it doesn't contain the character data, again write out that this is not a valid wave file. Okay, the next thing is actually something we care about. This is a 4 byte data, and it contains the size of the actual data. We obviously want to know the size of the data, so make the size equal to convert to int buffer 4. Right. And next is actual data. So let me create a character buffer, and I call it data, for example. And this will be a new char with the size of the size. Right, you may want to check if the size is, I don't know, -1 or 4 billion, because obviously you don't want to allocate that big of or that small of a memory. But for now I will just leave it to it. I hope it is the right data, so I just create one. Alright, and the last thing is actually return with the data, don't forget that, and pretty much that was the whole load wave function. So whatever I've wrote a comment here, you may want to check if these data are correct. And yeah, pretty much I hope the wave file is actually loaded right now. So here in the main function, if everything goes correctly, this loads the wave file. So now the actual OpenAL tutorial comes, because so far it was just C++. So first of all, I should mention how you can install OpenAL. If you are using Linux like I do, then you just go to the terminal, sudo apt-get or aptitude install and OpenAL, not OpenAL lib, OpenAL/dev. Yeah, /dev. This is it, and just install it and it will be installed. If you are not, then go to Google and so go to Google and write OpenAL tutorial right there, and the first link which comes up is the OpenAL website. I'm not sure if I can say it. It's not openal.com, it's something a little bit more complicated, but something about OpenAL, and there is a download section right there. You can find the binary for Windows and Mac there, so you just pretty much go there, download the binary, and as I looked it's an exe file, so you just pretty much double click it and install it in Windows. In Mac I have no idea. And you can download actually the source code right there, which is work for Linux as well. In that case you just go to the folder, press make, and then make install to install the entire file, and then you should be this should be installed. If everything goes correctly, you will have your header files in default in case of actually any operating system, the AL/something. So let me list out the file in /usr/include/al. This is not user usr, I said /include/al. As you can see, these are the header files for OpenAL in the OpenAL folder, and there are the lib files in my lib folder right here in the lib. If I grab the AL, anyway, here is OpenAL, so you can use the OpenAL flag when you compile the program. It may be platform dependent, so set your compiler or IDE to search the file wherever you have the include and lib files. Okay, so the files which I will use, so include the al/al.h, and the other is the alc.h, which is creating the context. I will talk about that in a moment. Okay, and what else? I include the SDL header file as well, so include sdl/sdl.h because of two things. One is to move the sound, and the other to give a little bit of delay to make the sound, so to give the sound a little bit of time to actually play. Right, and here in the main, let me actually start to program OpenAL. So the first free function call for OpenAL is pretty much just setting up the context. The context is pretty much what allows OpenAL to access to your sound card and use it. It's like SDL for OpenGL programming. We don't use SDL directly to program OpenGL, but SDL creates a context, so basically a window and somewhere where you can draw for OpenGL. So we use OpenGL, but OpenAL creates a context where you can draw. This is similar. So we have to create a context. To create a context, we don't use the AL like we usually do. Later on you will see, but we use the ALC. Okay, so let me show you the free line, because there is nothing too much to explain about this free line. So ALC device, this is a device, an ALC device, basically your sound card, and I just call it device, and this will be equal to ALC open device. This is the hardest part of the entire OpenAL, to set up this thing, and just pass null into here. You can pass a character literal right here if you know what you are doing, like you can pass direct sound, and it will try to use direct sound to access to your video card, which may prove useful, but I don't know why would you do that, but who knows. Okay, and just pass null, then it will pretty much try to open the default sound card with the default options. Okay, and if it is null, so device is equal to null, then just, I don't know, write out that stdcout cannot open sound card. Okay, and just make a new line and return with 0. Okay, next is to create the context. So ALC context, this is the name of the context, and you create the context from the device. So ALC create context, and you create the context from the device, and the second is null. These are flags, we don't care about flags. Okay, and again you can check if it is null. Actually, let me copy this because it's very similar check. Okay, and here just check the context if it is null, and cannot open context. Okay, and the last thing to do is to actually make this context current. So ALC make context current, and just have the context pointer right here. So I said this is pretty much, you have to do this free function call in every single OpenAL program which you do, and you may want to actually free these resources as well. So here in the end of the program, where is the end of the program? Here is the end of the program. I make return 0 here. Okay, here you have to destroy the context. So ALC destroy context, and then close the device. So ALC close device. Right, of course you should have the device and the context into here as a parameter. Now you have freed everything, so let me actually load the wave file to something like char and data. Okay, and before I forget, we should delete this data as well, because if you remember, we use the new to allocate space for this data. So here somewhere delete data. Right, before I forget, because I always forget to free the memory which I reserve. Okay, and pretty much everything is loaded, so we can use the actual OpenAL, because so far this was ALC OpenAL context, which is not really OpenAL. This is just for setting up OpenAL. But now we can actually start to create a buffer. Buffer is pretty much what contains the sound data. Does the source contain the sound data? But a buffer contains the sound data, and you can basically attach the sound data or the buffer to the sound source, not the sound source itself containing it. So now that I said, you see how much similar this function call is to the OpenGL version, AL gen buffers. As you can see, it's not generating a vertex buffer object, but actually generate a buffer which contains the sound. First parameter is how many buffers do you want to generate? One buffer, and where? So you give an address to an unsigned integer. So unsigned integer buffer ID. Okay, so I generate the buffer into the buffer ID. Buffer ID. Right, I have a buffer, so I should fill this up. So we use the AL buffer data function. As you can see, the function calls are pretty similar. Instead of using GL prefix, you use AL prefix. The naming and the capitalizations are pretty much similar. And later on, you will see that at the end of some function, you have the free F or free I or 1I kind of postfixes. Like in OpenGL, you have the same. Right, so the AL buffer data waits for the buffer ID first, which we have just created, so buffer ID. Then it's waiting for something called format. I will go into this format in a moment. I will create this format variable. Next is the actual data, which is data. The next is the size of the data, so size. So this is the data, and the size is returned with here, as you can see, convert to an integer. And the last is actually sample rate, so sample rate. These are the parameters which AL buffer data actually wait to fill up. Okay, so let me talk about this format. This format can be four things. It can be either AL underscore format underscore mono 8, mono 16, and similar with stereo 8, and stereo 16. So how can you decide what kind of format it is? Easily, you can use the bit per second as the last number, so it is 8 or 16, and you can use the number of channels if it is mono or stereo. I will use 4 if statements right here. So if the channel is actually 1, did I call it channel or channels? Channel. Okay, if the channel is 1, then this is a mono, else it is a stereo, and I use 2 more if here. So if the bit per second is 8, else if it is 16, and the same thing in here. Okay, and this will create the 4 constants. So here I will set AL format underscore mono 8, because it is a mono, because there is 1 channel and it is 8. Okay, then the format is equal with this. I create a format variable right here, which can be an unsigned integer, because this is just an enumeration value. It's a constant. You can store it in an integer. Right here the format is 16. Okay, and here the format is actually stereo 8, and lastly we have a stereo 16 right here, stereo 16. Okay, that was pretty much it. We have made this format variable, so we can just pass into here, and this will create what kind of format it is. Oh, we are almost there. We are almost playing the sound. Last thing to do is to actually create a source, a sound source. So I make another unsigned int and just call it source ID. For now, I have only one source, and you use the al gen sources function to generate a source. To generate a source, you pass the same parameter, so one source and into the address of source ID. Okay, and we are almost there. We have to attach the buffer to the source, so al source I. Okay, the al source is obviously the function which you use to set the properties of the source, and this I represents that this is waiting for one single integer parameter. It's not one I, as I would expect, it's just simple I. Okay, and first parameter is the source ID, so source ID which you want to set. Next is what parameter do you want to set? I want to set the al underscore buffer parameter, and the last is the actual buffer which you want to attach to this source, which is just the buffer ID. Okay, and last more code to actually play the sound. To play the sound, we use the al source play function. We're just waiting for the source ID. Okay, and actually we should give some time to it to play. So I make an SDL delay. I believe we don't have to initialize the SDL in order to use the SDL delay. I just add 5 seconds of delay because it's a 5-second long audio. Okay, and before I actually go, we should free the memory which we have reserved with the al generate sources and buffers. So actually let's delete those. So al delete sources, and I delete one source from the source ID. Okay, and al delete buffers, and I delete one buffer from the buffer ID. It is important the order, so first you free the source and then the buffer, or first you I believe this is it, because if you reverse the order, it writes out that it has to manually delete the buffer. Right, I think we are pretty much ready for a test. I think everything is set correctly, although I can't guarantee that. So let me just try to compile it. As I said, we need the OpenAL flag right here. And one thing, ALC create context, not kintext. Okay, let me get here ALC create context. Right, and we should use the LSDL flag as well. LSDL, just so we can use the delay. And if I run it, apparently nothing is happening. Why is nothing is happening? Of course nothing is happening. I forget to read in the data, I believe. So this is our only problem. So in .read, I read into the data with size data, and I believe this should fix the problem, although I can't guarantee that. Yes, it does actually fix the problem. I forget to read in the data, which is the most important part of the entire wave loader. Forget it. Never mind, it actually played the sound. I'm not sure if you hear that or not, but if I just put this microphone closer. Perfect, that's actually working. So now we can actually delete this line. Okay, and now we can actually try to move this sound in the 3D space. I will be back in a moment. Alrighty then, I just copied in a SDL main loop right here. As you can see, this while running stuff. If you're not familiar with SDL, basically all I did here is create an endless loop basically here in this outer loop. And then if I press the up, down, right or left key, I just set the boolean value to true. This boolean array, I have it here with 4 elements. So this first boolean is true if the up key is pressed, and then the right key, down key and left key is pressed. And then I can read in these values to move, for example, the sound position. So let me immediately do that. So we'll create an x and z variable, and let me actually initialize it to 0 and 0. Perfect. I have 2 variables, an x and a z, and I can use this x and z variable to set the position of the sound source. So right here, if the up key is pressed, so B0 I said, then I just move this in the positive z-axis, so z plus equal 0.3, and actually make another if B1 is pressed, then if I remember correctly, that would be the right key. If the right key is pressed, then I move it to the positive x direction, so x plus equals 0.3. Perfect. Then if the B2 is pressed, the B2 is actually the down key, so Z minus equal 0.3, and lastly I have the B3, which is the left key, so X minus equal 0.3. Okay, so here I just change the coordinate according to which key is pressed, and let me set the position of the sound source to that. So AL source 3F, again I said this 3F is same as in OpenGL, meaning that there are 3 floating point numbers with this parameter weight besides the obvious one. So we need the source ID, which source I want to modify, then which property do I source want to modify. So basically I want to AL position, which is obviously the position, and last the X, Y and Z coordinate. Alright, and I actually set the playing to the space key. Oh, and by the way, I didn't mention that there are other functions besides play, which are the stop, pause, and rewind. These are, I think, all, and this is pretty much does what you expect them to do. So stop the music, pause the music, and rewind, start the music from the beginning. Okay, so I just played the source, and then let me actually compile this. If I can, and run it. And I put the microphone closer and I try to move the sound. Alright, one thing that I should make it float, because if I add or subtract 0.3 from an integer, then it will be just 0. That's why you didn't hear the change. And yeah, okay, so now if everything goes correctly, and it would, then you will hear that as I make the source far away, it will be quieter. So let's listen. As you can hear, it immediately gets farther away. Other things are alright. We can make the sound source looping actually, so it will make a continuous noise. I don't know, for example, in case of a car, the engine is continuously going. To make a sound continuous or looping, you can set the source value, so GL source I, and again source ID, and the second parameter is the looping variable, so AL underscore looping. This variable is basically set true if looping, so you can use AL true or AL false to set if it is looping or not. So now if everything goes correctly, I can compile it, and when I run it, it will continuously looping through. So as you can hear, it continuously starts over and over again without I have to press the space. Oh, by the way, one thing, that if I press the space several times while the last source is actually playing, it will not mix those two together, but actually restart the source from the beginning. So if I continuously pressing, for example, the space, then I don't hear anything, because it's just start and stop and start over again, So it's an important thing to make sure that you don't want to play a source which is already playing. Of course, if you don't, if you could have a reason for that, but usually you want to avoid this situation. Alright, we can actually set the listener parameter, because so far we just set the source parameter, and these are the most important parameter. You can set the velocity of the source. You might think what this velocity is actually for, and this is for calculating the Doppler effect. Probably you already heard what Doppler effect is, and this is basically when a car or an airplane or something with high speed going toward you, and when while it's going toward you, its sound is higher pitch, and when it goes away from you, it's lower. So, you know, like in a Formula 1 car or Formula 1 car or something. Right. Cool sound effect, by the way. Okay, so you can set the you can set the velocity, and these were the most important ones. And now let's set the listener. Listener mostly has the same parameters which you can set. So you can set the position of the listener, what else, you can set the orientation of the listener. To set the orientation, this is not as simple as calling AL listener 3f, because it doesn't wait 3 floating point number, but actually waiting 6 floating point number. That's not 6f, but actually fv, like a floating point vector, similarly than in OpenGL. Okay, the listener don't have an ID, so you can just pretty much omit the first parameter, and the second parameter is al underscore orientation. And this orientation is basically waiting for a floating point number, so pass f there, and then create an array with 6 elements. The first 3 elements is actually the actual orientation, so where your player is looking at, the looking direction. So for, I don't know, like 1, 0, 0, it's pretty much meaning that the listener is actually looking at the positive x direction, and then an up vector is needed as well, which is 0, 1, 0, so the up vector is actually the positive y direction, for example, and it will tell OpenAL where the listener is looking at. By the way, a listener is basically you, the player, or a speaker, or whatever. That basically there is just one simple listener, so you don't have to initialize the listener. Okay. That doesn't hear any change, but sure there is something. And what else can you set? You can set the position to be relative. There is not too much left, because mostly we just covered basically everything. It's not so complex material. If you want to know more, obviously you have to go to the website, and there is a documentation section there on the left side at the bottom menu. This is documentation. Click on it and you will find an OpenAL 1.1 manual or something, which describes all of the functions and all of the possible constant values with a little text without actual practical example. But now that you have the basic program, the base program, you can just play with those constants and values and so on. The purpose of this tutorial is not to show every single possible constant which you can use and every single possible function calls, but to set up an actual OpenAL program which you can later on extend. By the way, I might not mention that, but I use OpenAL in the FPS game. It's much better. There is not that annoying delay, because with SDL Mixer there was a 0.3 to 1 second delay between when I actually call the function and where the sound started to come out from the speaker, which was ridiculous. It's just unacceptable. It doesn't work for an FPS game. It may be okay for a simple 2D game, but for a 3D game it doesn't really work. So that's why I changed it to OpenAL, and it's much better. There is no delay, and it's working correctly. Okay, one thing I think I shouldn't mention is that if you have a stereo type, so here either stereo 8 or stereo 16, I think the position calculation and so the position and attenuation calculations are not applied to stereo sources. So you want to use mono sources if you want to apply to some object or enemies or weapon or something. You should use stereo only if you are if you want to use background music, for example, or something similar. Okay, that was pretty much it. I hope you enjoyed. Thank you for watching, and have a great